Welcome to the deep dive. Today we're going deep, really deep into white dwarfs. You know, those incredibly dense remnants left over when stars like our sun finally run out of fuel.
Yep, fascinating objects. And for this dive, we've gathered quite a bit of material, especially focusing on the revolution brought about by the Gaia space mission.
Right, so we're looking at some key research papers of Babuzio et al., Bergeron et al., people like Tremblay, Eisern, Killick, Wingett.
Yeah,
Quite a list.
exactly. Foundational work and the latest stuff building on it.
And our goal here really is to unpack what these sources tell us. How is Gaia's amazing precision, changing how we think about white dwarf physics? Their structure, how they cool down, what they're made of?
And there are some genuinely surprising things popping out of the data, things we maybe didn't expect.
Okay, let's start with the basics then, just to ground ourselves based on these sources. What's
Yeah.
the typical structure we're talking about?
So the core idea is this incredibly dense, degenerate core, mostly carbon and oxygen for the common types. That's where nearly all the mass is, and it holds the leftover heat, the thermal energy.
And that heat doesn't just vanish instantly, right? There are outer layers controlling its escape.
That's right. The sources describe this surrounding envelope, which is also partly degenerate, and it's layered. Usually there's a helium layer, maybe about, say, 1% of the sun's mass sitting on that core.
Okay.
And then right on the surface, an even thinner hydrogen layer. Could be absolutely minuscule, like 10 to the minus 15 solar masses or, up to maybe 10 to the minus 4. Still very thin, but a huge range.
And these things are pretty uniform in mass for a specific type anyway. The sources seem clear on that.
Yeah, remarkably so. If you look at the DA white dwarfs, those are the ones showing hydrogen lines in their spectra. They really cluster around 0.59 times the sun's mass. It's a sharp peak.
And the DBs show helium instead.
Correct. DA for hydrogen, DB for helium. Then you get other types like DC, which show almost nothing, so on.
And evolution-wise, it's just cooling for a really, really long time.
Pretty much. They just sit there radiating away that leftover heat. We're talking like 10 billion years, sometimes more.
Yeah.
The sources break down the cooling into stages, depending on what's dominating the energy loss.
Okay, what are those?
Well, early on, it's neutrinos escaping, carrying energy away. Then you get what's called fluid cooling. After that comes crystallization, the core freezing, and finally Dubby cooling, which is related to the crystal structure.
But it's not just a simple checklist, is it? The sources mention complexities.
Oh, absolutely. Things like convection kicking in or heavier elements, maybe sinking down sedimentation. These processes, as papers like Eisern discuss, definitely complicate the simple cooling picture. They modify the rate.
Right. So enter Gaia. How did it shake things up? That Babuzio et al. 2018 paper seems like a milestone.
Huge milestone. They took Gaia's second data release, DR2, and got incredibly precise distances for, 26,000 white dwarfs. Really clean sample.
Yeah.
And they plotted them on an HR diagram.
The Hertzsprung-Russell diagram. Luminosity versus temperature, basically.
Exactly. The classic tool. For white dwarfs, it maps their cooling path. And Gaia's precision just, wow. It revealed features with a clarity we'd never really seen before.
Okay, so looking at that diagram in the sources, what's the first thing that grabs you?
The separation. Just how cleanly the different types split out. The DA white dwarfs, the hydrogen ones, they form this really tight, distinct sequence. And the non-DA types, the helium ones, they sit clearly apart.
Not just a fuzzy blur.
No, not at all. Especially in a particular color range Gaia measures is a really sharp division. That gives theorists something solid to aim for with their models.
And that main DA sequence, you said it was tight?
Incredibly narrow. That's the direct observation confirming that mass peak we talked about, around 0.6 solar masses. Most of them seem to be born right around that mass.
Did they see anything else interesting on that plot?
Yeah, there were points scattered above the main sequence.
Yeah.
The sources identify these pretty clearly as white dwarfs in binary systems. Two stars together look brighter than one.
Makes sense. And wasn't there a bend or a kind of feature within the sequence itself, labeled Q?
Yes, that sloping band feature. And the immediate interpretation of the source was core crystallization, the point where the inside starts to solidify.
Okay, so Gaia sees the signature of the core freezing. Now, Bergeron et al. Took this even further in 2019.
They did. They refined the sample, even more stricter parallax limits, kicked out known binaries, really trying to isolate the single white dwarfs.
And did that change the picture?
Well, it confirmed that sharp split between DA and non-DA stars, maybe even made it look starker. But, and this is key, it really highlighted a puzzle.
Oh.
When they compared the positions of these stars on the HR diagram to the theoretical models, Models assuming pure hydrogen atmospheres or pure helium atmospheres at different temperatures and masses, something didn't line up.
The models didn't fit what Gaia was seeing.
Well, for the DA stars, the pure hydrogen models, especially around that zero.6 solar mass mark, fit beautifully. Just trace the observed sequence perfectly.
Okay, so far so good.
But the models for the non-DA stars, assuming pure helium atmospheres, they didn't land where the actual non-DA stars are observed. In fact, the theoretical pure helium sequence slices right through the gap between where we see the DA and the non-DA stars.
Whoa, okay, so that's a problem. Pure helium doesn't work for the non-DA guys. Abluzia had already hinted at this, right? Maybe bad models, or maybe they were heavier.
Exactly. Bergeron et al. Really dug into that second idea, the mass possibility. They split the sample, DA and non-DA. DA stars, like we said, 50.6 solar mass, pure H model, well.
Although they did see some that looked like really low mass stars.
Right, less than maybe zero point 0.4 solar masses. But the conclusion in the sources is that these are almost certainly unresolved pairs of white dwarfs, double degenerates. They look like one object, appear brighter, and so get misinterpreted as single, low-mass stars.
Okay, so setting those aside, what about the main group of non-DAs, the DBs, DCs, etc.?
Well, if you stick with the assumption that they have pure helium atmospheres, then to explain why they sit where they do on the HR diagram, their brightness for their color, you're forced to conclude they must be significantly more massive than the typical DAs.
So pure helium implies heavier non-DA stars. Is there another explanation offered?
Yes, and this is the really neat insight highlighted in the papers. Maybe you don't need those high masses at all. Maybe these non-DA stars are actually normal mass, around 0.6 solar masses, but they just have a tiny, tiny trace amount of hydrogen mixed into their helium atmospheres.
Just a little bit of hydrogen contamination. How does that fix the mass issue?
It dramatically changes the atmosphere's opacity, how easily light gets out. Even a trace amount of hydrogen affects that calculation. So when you observe the star's color and brightness and try to figure out its temperature and luminosity, that trace hydrogen changes the relationship.
So it affects the interpretation of the observations.
Precisely. If you account for even a little bit of hydrogen in the models, suddenly the observed positions of the non-DA stars match models with much more standard masses, back around that 0.6 solar mass average.
Wow. So a tiny atmospheric detail could solve a big puzzle about their fundamental properties. And the source connects this to other work, right, like Killick et al., suggesting maybe lots of massive white dwarfs from mergers. Does this trace hydrogen idea reduce the need for those?
It definitely raises the question. If many non-DA stars aren't actually that massive, just hiding trace hydrogen, maybe we don't need as many exotic formation channels like mergers to explain the population. It's flagged as an open area of research, Gaia's data pushing us to reconsider.
Okay, fascinating. Let's circle back to that Q band, the crystallization signature.
Yeah.
How exactly does Gaia see the core freezing? You mentioned a pileup.
Yeah, it's a population effect. When the material in the core starts to transition from liquid to solid crystallizing, it releases energy, latent heat, just like water releases heat when it turns to ice.
Okay, extra heat source.
Right. And that extra energy temporarily slows down the star's overall cooling rate. It means the white dwarf spends a little bit longer at that particular temperature and luminosity before cooling further.
So more stars hang out in that part of the HR diagram, creating a denser region, the pileup that Gaia observes across thousands of stars.
Exactly. You can see this in the theoretical analysis too, like in Bergeron et al. They use cooling isochrones, lines of equal age on the HR diagram. Where those lines bunch up, cooling is slower. Where they spread out, it's faster.
And the sources show that bunching up right where crystallization is expected.
Precisely. They often show two curves. A lower one where crystallization starts in the very center, and an upper one where maybe 80% of the mass is solid. And the isochrones get really crowded between those curves. That's the slowdown from latent heat, matching Gaia's observed Q-band pileup.
But crystallization isn't the only thing happening around then, is it? The sources mention other effects modifying the cooling.
Correct. Two other important ones are mentioned, Debye cooling and convective coupling. Debye cooling happens later in the already solid core. It's a quantum effect related to how vibrations travel through the crystal, and it actually speeds up cooling again.
Okay, so speeds up after the slowdown. What's convective coupling?
That also speeds things up. It's when the convection zone near the surface, the churning layer that transports heat, digs deep enough to actually connect with the degenerate core. It basically opens up a highway for heat to escape more efficiently.
So you've got crystallization slowing things down, but Debye cooling and convective coupling speeding things up. Sounds complicated.
It is. And the challenge, as the sources point out, is that for a typical zero point 0.6 solar mass white dwarf, the crystallization phase and the onset of this convective coupling seem to happen around the same time as similar luminosities.
Making it hard to tell them apart just by looking at the overall shape of the cooling sequence in the HR diagram.
Exactly. It's tough to disentangle the exact contribution of each effect just from that population view. Lots of physics happening simultaneously.
And eventually, way, way down the line, they cool off completely and become hypothetical black dwarfs. But none exist yet.
Right. The universe just isn't old enough for that yet. We need much more time.
Okay, so Gaia gives us this amazing population view of crystallization. But what about seeing it in individual stars? Do the sources talk about that?
They do, and it's really critical. Because, as the sources emphasize, the details of crystallization, exactly when it starts, how much heat gets released, these uncertainties can throw off the age estimates for the very oldest, coolest white dwarfs by like a billion years.
A billion years. That's significant if you're using them to date parts of the galaxy.
Hugely significant. They're supposed to be reliable cosmic clocks. So nailing down crystallization physics is vital.
The sources bring up an old case study, BPM 37093. From way back in 1997, Wingett et al. Suspected it was largely crystallized.
Yeah, based on its properties, it's a massive white dwarf, and it pulsates. Its position on theoretical cooling tracks developed by Wood suggested it should have a very large crystallized core, maybe over 90% solid, even back then.
And they had ideas for how to check that using its pulsations, asteroseismology.
Right, listening to the star ring like a bell. They proposed two tests. One was looking at the precise spacing between its pulsation frequencies, the notes it rings with. Theory predicted this spacing would change depending on how much of the core was solid versus liquid.
Okay, and the second test?
Measuring the rate of change of a pulsation period over time.
Mm-hmm.
Because the crystallization front, the boundary between solid and liquid, moves outwards incredibly slowly, like centimeters per year, it should cause a tiny, tiny drift in the pulsation periods. They figured it would take maybe 10 or 20 years of steady observation to detect it.
So fast forward about 20 years, Corsico et al. In 2019 revisited this.
They did. And they didn't just look at BPM 37093. They did an astroseismic analysis of three very massive pulsating DAs, BPM 37093, GD518, and another one called SDSSJ0840 plus 5222. All are over a solar mass, around 12,500 Kelvin prime candidates for having substantial crystallized cores based on the models.
And what did the seismology find? Did it confirm the crystallization?
It provided really strong independent evidence. They estimated the crystallized mass fractions, about 92% for BPM 37093, a whopping 97% for GD518, and 81% for the third one. These numbers fit very well with what theory predicts for stars of that mass and temperature.
That's pretty amazing confirmation. Now, asteroseismology can also give distances, right? As a cross-check with Gaia.
It can, but here's where another little puzzle emerged, mentioned in the sources, specifically for BPM 37093.
What was the issue?
The distance Corsico et al. Got from asteroseismology was about 11.4 parsecs. But the Gaia DR2 distance measurement for the same star was significantly distant, around 14.8 parsecs.
That's quite a difference. Any ideas why?
Well, the source speculates a bit. It touches on the origin of these ultramassive white dwarfs. Are they the end result of single massive stars which would likely leave behind oxygen neon cores? Or do some form from mergers of two smaller white dwarfs, which would result in carbon-oxygen cores?
Could that core composition difference affect the pulsations or the distance estimate somehow?
It's possible. The source hints that maybe this discrepancy for BPM 37093 is related to its formation history or internal composition in ways we don't fully understand yet. It's definitely flagged as something needing more investigation.
Okay, so let's try to pull all this together. What are the main headlines from this deep dive into the sources?
Well, we started with the basic structure, cooling phases, then saw how Gaia's view, particularly in the HR diagram from Babusio and Bergeron, just transformed our understanding. We saw that clear separation of types, the narrow mass peak.
And crucially, that Q-band pileup, the direct population signature of core crystallization slowing things down.
Exactly. Then there was the puzzle of the non-DA stars. The pure helium models just didn't fit. And the potential solution seems to be adding just a trace amount of hydrogen, which neatly fixes the inferred masses, bringing them back to normal.
Right, avoiding the need for potentially too many massive merger-formed white dwarfs.
Then we looked closer at the cooling physics crystallization releasing heat, but also Dubby cooling and convective coupling speeding things up later, making it complex to disentangle.
And finally, the asteroseismology work, like Corsico et al.'s analysis of massive pulsators, giving independent, strong evidence for large crystallized cores, confirming that picture, even with some remaining wrinkles, like that distance discrepancy for BPM 37093.
Yeah, it really paints a picture of progress, but also ongoing questions.
It really shows how these huge surveys like Gaia, giving us the big picture, work hand in hand with detailed studies of individual stars using techniques like asteroseismology. White dwarf physics is clearly complex, but Gaia is showing us the consequences in beautiful detail.
Absolutely. The precision is just phenomenal.
So here's a final thought to leave you with, based on what we've discussed from the sources. We heard that crystallization uncertainties can affect age estimates for the oldest white dwarfs by maybe 1 billion years. These stars are our clocks for dating the galactic disk. So as Gaia, astroseismology, and better models continue to refine our understanding of exactly how these stars freeze from the inside out, how might that ultimately redraw our map of our own galaxy's history?
That's the big question, isn't it? Really makes you think about how interconnected it all is.
Indeed. Thank you for joining us for this deep dive.